Welcome to lecture 1D of the Advanced Computer Architecture and Advanced Microprocessor System course. Now, today we are going to be looking at the Vivado based Artix 7 FPGA board user guide. You've seen the FPGA board we are going to use. You have already looked at it and then the components that are within the FPGA board. We have also looked at how to install the Vivado tool and how to acquire the license. So after we've installed the tool and acquired the license and know how the board works, we are going to take a design example that will implement very or simple logic gates using the FPGA board. So here for you will design Verilog code for three gates and gate or gate XOR gate. We will design Verilog test bench for the gates design, and then we will implement the design on the FPGA board. Right. So first, we have to open the Vivado tool. Double click on the Vivado tool to open it. It takes some time to open based on um, the speed of your computer. So if your computer is slow, it will take a very long time before it opens. If you have a very fast computer, then it takes a very short time to open. So let's wait for it to open. So it is opening. Okay, so this is the Vivado tool, and this is the interface that first starts. This is the interface you see when you first open Vivado tool. So now the first thing you have to do is to create a new project. So just click on create new project. And then this create new project wizard will appear, and you will just click on next and select your project name, give it a meaningful name. So here you are actually designing logic gates. So what you do is that you just name it gates. So any name will do here, but just give it a name that actually mimics your design. So go to next. So it's saying this gate already exists. I've already designed this already. So once it already exists, you have to choose a new name. Gates, let's say gates. We want XOR gate underscore XOR gates and or and then from here we are doing we are doing an RTL project. The RTL just means that it is a register transfer level, so that's what we're going to use. Then click on next. Here we can add sources if you have a design like where code already existed. We can easily add it here, but since we don't have any Verilog code at the moment right now, we have to click on next. And then we don't have any constraint file. This is where you add the constraint file, that is the connections or the pin mapping from the FPGA board to any component from the FPGA wire to any component on the FPGA board. We don't have any pin mapping for now, so we just click on next. Here, this is actually very important. Here is where you select the FPGA device. Each FPGA device here has a name. Right, so if you don't select the right FPGA device, you cannot actually be able to program or to load your code onto the board. So you have to be very careful here when selecting. So here, what we are using is the FPGA device is the XC735T FTJ5 6-1. This is the FPGA device we're using. So we have to go and search for it in the Vivado tool. Right. So all we do is that we come here to select the family. The family is the Artix 7. So we click on that. Then the package is the FTG256. FTG256. It means that we have 256 input output devices. The speed grade is -1. Now you come and see that our XC7A35 TFT256-1 is here. So just select it and then click next. And then here it will give you the summary of uh, of your project or the project you're going to design. It give you the parts, the product, the family, the package, the speed rate, and then it give you the name of the project. And then it says that there are no sources and then no constraint file. So we are going to create it from the scratch. Then you just click on finish. So once we are done, this is the interface we get. Now here we have the project navigator. This is actually the design flow of the FPGA. You can see we have simulation, actual analysis, synthesis, implementation, and then program. So that's the design flow. We have the project manager here. The project manager lists the sources. If you have some design sources, if you have your design or your design code, it will be located here. Your constraint file, that is your pin mapping to the FPGA board, will be located here. Your simulation sources will be located here. The summary of the project is on this panel. You have some dashboard that will give you some the design results, and then you have your design rounds here. You have a ATLC console. We have messages, your error messages, and stuff like that will be seen here. And then your reports. If we generate utilization report, that is the gates we are using, or the logic gates and everything, to report how many logic gates and or how many components the of the LUTs are being used. It will all be reported on this tab. Right. So first we want to add or we want to create a design source. We want to create a design source. So what we do is that we come and click on this plus sign here. You, you can do it. You can do it several ways. You can also come and add sources, but I prefer to click on this plus sign here, and then it will come to it will open a panel. Now here you have three choices: to create a constraint file, to create a design source, and then to create simulation source. The, the constraint file is the pin mapping. That is the connections from the FPGA board to the components, or for instance the sub-segment display, the dip switch or whatever we're using. The create design sources are your Verilog code you're actually creating, and then create simulation sources after you've created um, your design source, which is the Verilog file. Then you create some simulation sources to be able to simulate and see what is happening to your design. So here we are going to first of all create our design source. So you click on it and then go to next. Now here we don't have you can add a design source or you can create a design source. So you come and click on create design source and then give it a name. So first name are you going to give it? So just say gates, because we are just going to design some logic gates, and click on OK. Now we click on finish and click on OK. Yes. And your design source is created. Now if you come in to your design source here, you see the file located here, which is gates. You just double click it, and then it will open your editor for you. Now this is a custom editor I'm using. So this is not the default editor of Vivado. So if you want to use a default editor, you just come here, go to settings, and then go to editor, and then choose what editor you want. You can use the custom Vivado editor, or you can come and choose custom editor here, and then use whatever editor you want. Right now here, go and find out how to use just any of your favorite editors you want to use. You can come and input those the source, or where that editor is located in this text box here, and just click OK. So I'm using the Notepad plus plus, which is this one, right? So now once you open your gates, there is nothing in it, right? So you will now have to now define what will be inside your gates, and then what we are going to do is we are going to design um, what we're going to design is an AND or an XOR gate, which can be seen on the board here. We are designing an AND gate, we're designing an AND gate, we're designing an OR gate, and then we are designing an XOR gate. This is our design. Now, all the designs have the same input, which is input A and input B. So the AND gate has input A and B, the OR gate has input A and B, and then the XOR gate has input A and input B. The output of the AND gate is X, the output of the OR gate is Y, and the output of the XOR gate is Z. Right. So this is what we are going to design. So we have three gates, AND or XOR, with inputs A and B, and then output of AND is X, or is Y, and XOR is Z. So that's what we are going to design. So first of all, what you do is in your text editor, you first of all define your inputs and outputs. So we have inputs A, B, which are these inputs A, B, and then we have our outputs X, Y, and Z. Those are our outputs, right? So AB is our input, XY is our outputs. Okay, so now from here, I think it's important we actually use comments so that everybody understands, because so we have to come and declare our input and output. So input and output de declaration, right? So this is, as you know, the declare is just a comment. This just means a comment, and then you can use backslash and star to also mean a comment. So, but because it's just one line, we can just use double backslash here um, to just show that it's a comment. Now then from there, you are defining our input first. So you come and type input A, B. So it means that we have two inputs A and B. Then we have outputs X, Y, Z. So yeah, these are our input and then our output. Now we have to now come and declare our gates. So just gates declaration. Here, our first gate is the AND gate, right? And then here we are going to use I think you already know the symbols for an AND gate in most programming languages, right? The symbol for an AND gate is the symbol for an AND gate is this. The symbol for an OR gate is this. Just one bar, and then the symbol for an XOR gate is this. Right? So those are the symbols we're going to use for an AND gate. So, and then this operates on only one bit. So as we have one bit here, this will work. So this is the symbol for an AND gate, the symbol for an OR gate, and then the symbol for an XOR gate. You'll be seeing this very soon, but this tutorial is just to help you use the Vivado tool and make yourself ready for the actual coding. So here, our first gate is the AND gate. So I'll come and type assign. We're going to assign and then the output of the AND gate is X. As you can see here, our output is X. So assign X is equals to A and B. So it's that simple. Just assign X is equals to A and B, right? And from there, we want our OR gate. So we assign Y is equals to A or B. And then again, we want XOR. So assign Z is equals to A XOR B. And we are done. So we have declared our three gates and or XOR. And then we have assigned our inputs and outputs to those gates. So we just save this and and our next step is to actually synthesize, right? So you come here. Now, first of all, you can actually elaborate your design to see if your design the interconnections were actually correct. So you just come to actual synthesis, right? Then click on label design, then click on OK. It takes some time for it to be generated, so you have to be patient with it. So it is elaborating the design. Right. So this is the elaborated design. As you can see very clearly, we have an AND gate, an OR gate, and an XOR gate. So this is just to check to see if your design was able to use the gates you implemented. or the gate you want it to use. So the gate just functional level, right? Now here you're going to synthesize the design, and after you've elaborated your design, the synthesis just means that these gates are not the FPGA board is not going to implement directly on this gate. But as I said, the FPGA board consists of what is called or what is known as LUTs. So the your design is going to be implemented using LUTs which are located on the FPGA board. So this elaborated design is not what is going to implement directly, but what after we synthesize it is going to use the resources available on the FPGA board, which are the LUT. So that is where your design is going to be, or your design is going to be implemented inside the LUTs of the FPGA board. So you have to come here and run synthesis. It also takes some time for it to run, so you have to wait for some time. You can close this elaborated design for now. Okay, now after it's done, you come and click on open synthesize design. Want to see the what the design synthesized to, or what components of the FPGA our design is going to use. So click on OK. Now this symbol here is what is the netlist. So just click on it, or the schematic of the netlist. So this is what it's implemented to. So it uses LUT to connect our input to our output. So this LUT, inside this LUT will be some kind of, as I said, a multiplexer and then data input. So the functions will be stored inside the data input, and then the multiplexer will actually bring out one of the input based on one of the stored data based on the input we actually give it. So this is how it actually does it. And as you can see, it uses some buffers to connect the input and then the output also. Right. Now after your design is being has been synthesized, you can go and look at a summary of what the design used. Right. Now when you come to the utilization here you can click on the table to see how many LUTs we use. So here it estimated that it used two LUTs. Then we have a total of 2080 LUTs. So the utilization is 0.01%. And then for the input output, it used only five because we have A, B, X, Y, Z. So five IO. And then the total IOs are available to the user is 170. So you need to take notes of these resources. So you don't the available LUTs is just 20800. So you don't have to go beyond this 20800. Right. Now from here you can just close your synthesize design, and then we move on to the next step. Now our next step is to design a test bench for this simple X and XOR or gate that we've designed. So how do we start by designing our test bench? Now to design our test bench, we have to first of all draw the truth table for the AND XOR and OR gates. So we have two inputs here, So we have two inputs. So we have A, input B, and then we have three outputs X, which is for the AND gate. We have Y for the OR gate, and then we have Z for the SO gate. So the inputs 0, 0, 0, 1, 1, 0, 1, 1. Right. Okay. So here for X is an AND gate, and then for the AND gate, the truth table for an AND gate indicates that if there's a zero, if A is zero and B is zero, we have a zero. If A is zero and B is one, is zero. A is zero and B is zero, zero. A is one and B is one, we have a one, right? And then for an OR gate, we have zero, one, 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 and then for an XOR gate, we have 0, 0 is 0, 1, 1 is 0, and then 0, 1 is 1, and then 1, 0 is 1. Alright, so this is going to be our test vectors. A, B will be our test vectors. So you have to design our test bench, and then we have to input 0, 0, 0, 1, 1, 0, and 1, 1 as our test vectors, and see the outputs X, Y, and Z if they match this. So let's see our test bench design. So to design our test bench, first of all, we have to go through the plus sign again, which is here. Just click on the plus sign. Now here, instead of add or create design sources, we have to come to add or create simulation sources. Click on next, click on create file, and then gates. Just like let the simulation file name match the variable file name. So gate, and then get do it underscore tb. So that this file will be known as a test bench file. So it's gate underscore test bench, gate underscore tb, right? Click on OK, then click on finish. Okay, then yes. Okay, so once we are done here, you will you will see that you come to your simulation sources, click on it, then you see that your gate is located here. Your gate.testbench is located here. So you just double click it. Again, it will be empty, right? So you have to come and fill it up. Now for the simulation, there's no input output here. You just so for the input, you first of all start with the inputs are registers inside the simulation file. The inputs will be declared as registers. So register A, B, and then the outputs will be declared as YS. So Y X, Y, Z. Right. Now come and come and initiate the we call it unit and test BTT. unit and the test is the gate we design. This gate is initiated by calling it. It's just like function call. So gate, um, give it any name you want. Maybe UTT, and opening and close bracket, and then the connections within the gate. Now, the gate here has a connection has two inputs. We have A, so you use dot A to connect it to the input here, A, right? Then we go to dot. We have another input dot B. Within this gate will be connected to B in the test bench, and then for the output dot X, they are the same names. Dot X will be connected to X here, dot Y. The output in the gate will be connected to Y, and then dot Z will be connected to Z, right? So we have instantiated our gate here. Now, um, we need to input some test vectors. We will start off with a statement known as the initial begin. You will see you understand all of the version, but this is just to make sure that you understand how to use it to before you begin coding. So initial begin, and then we define our test vectors here. So our test vectors are the A and B values. So the A and B values here are our test vectors. So we come to A is equals to, so the first one, A is equals to 0, B is equals to what? 0. And then a very important matrix. This is the timing, 100. So it means that we give our input A to be, we make our input A to be 0, our B to be 0, and then we wait for 100 nanoseconds. This means 100, we wait for 100 nanoseconds before we change the inputs again. The next one is our A is 0, B is 1, and then we wait for another 100 nanoseconds. Then our next one is A is 1, B is 0, wait for 100 nanoseconds, and our last one is A is 1, B is 1, and then we wait for 100 nanoseconds. So this is just what the test bench is, right? So now, after our test bench has been designed, we need to actually do our simulation. We just have to come back to the Vivado tool. This is our test bench here. Now we come down here to simulation, right? We come to run simulation and run behavioral simulation. We have different forms of simulation. Now we are doing only behavioral simulation to see if we give it an output, if we give it an input, does our output match with our truth table here? So we give it our input A, and then we'll see how to see if our output match with our truth table that we designed here, right? So just come to run behavioral simulation. So if there are some kind of errors, it will show up in the console. Just go to the messages on on the console and then or on the TCL console, and it will say that oh, the simulation have failed. But did it why did it fail? You go through the errors. So gate is not found. So you see the model name gate is not found. We use gate, but the model name is gates. GITES, but we use gates, so you have to come back to your design. Here it's not gates, it's gates. Right. Save it, then come back to your simulation. Here, run simulation, run behavioral simulation. So these are the little errors you'll be seeing, and then you just go to the TCL console to see what the error message is, and then you go back to your code, correct it, and rerun again. You'll be seeing it a lot. You'll be making simple mistakes, and then you'll be correcting them a lot. Right. So now this is the simulation waveform it has opened for us. Right. So you can just click on this to just zoom into all the simulations. So first of all, we start from this is 0 nanoseconds to 100 nanoseconds. So for 0 nanoseconds to 100 nanoseconds, A is 0, B is 0, X is so if A is 0 and B is 0, we know that from our truth table, X is 0, Y is 0, Z is 0. So you can see that from here, X is 0, Y is 0, Z is 0. Now once we come from 100 nanoseconds onwards, um, our A is 0, B is 1, right? Once A is 0, B is 1, our X is 0, and then Y is 1, and our Z is 1. So we have 0, 1, 1. So that is correct. We move on to our next 100 nanoseconds. Our A is 1, our B is 0. So our X is 0, our Y is 1, and our Z is 1, which is also correct. Then the last one, our A is 1 or B is 1. If A is 1 and B is 1, X is 1, Y is 1, and Z is 0. 1, 1, 0. So that is also correct. So we have seen that our simulation actually matches our truth table. So we can close the simulation waveform because we are okay with it. So now our next step is to match our next step is to match the the components on the FPGA board, or to match our design on the components of the FPGA board. Now this is the FPGA board. This is where our logic lies, our AND or XOR gate lies here. But now we want to bring we want to give it inputs, and then the FPGA will work, and then the FPGA gives out an output. So how do we actually do this? Now, first of all, we have to define the components. Which components are we going to use? Which components on the FPGA board are we going to use? So in my design, I'm going to make sure that I'm going to say that I'm using the diff switch as my inputs. The diff switch will be my A and B, and then I'm using three LEDs to represent my X, Y, Z. So X, Y, Z will be the three LEDs, and then the A and B will be two diff switches. So if I click or if I push this switch up, it just means that one I've inputted a one. If I push this switch down, it means that I've inputted a zero. So that is what I'm going to be using to map our design to the components of the FPGA board. So um, I'm using the switches, and then I'm using the LEDs. So there is to be able to map your APG to components, you have to use what is called the XDC file. The XZ file has all the pin mappings, the pins that have to the pins that map directly from the FPGA board to each component you have. So when you look at the XDC file, if you go, you can go to the website of this board and check out the SDC file. This is the Edge 87 FPGA kit SDC pins details. So all the pin connections are here. So here, if I'm using this, the switches are actually 16 in number. As you can be seeing here, they're about 16 from the LSB to the MSB. So the ones I want to use, I will just actually copy and go and paste them into the files in my Vivado constraint file, and then the rest I don't care about. Now I'm using only two of the switches, so I need only two of this, and then the LEDs are also 16 in number. As you can be seeing here, this is for the LED 16 in number. So I can copy the number of ones I want to use, and then all I have to do is change the name. These names must actually match These names must match the name inside my code, as you'll be seeing very soon. So here, what I do first of all is that I go again, I click on my plus sign here, go to add or create constraints, next create constraint, and then I name it this underscore pin map. Any name will do, but just make sure that the name matches your design, right? Click on OK and then finish. Alright, so when it's done, the config file will be located here. So you just double click it and it will be empty. There was nothing to it. So you go and copy from this site. Go and copy from this site here and paste it inside your pmap and page pmap.xz file. I've already done that, and then as I said, the name must match. So this is A B. So this is A B, which matches our gates here, which matches our gates here A B, right? And then we have our our output to the LEDs are X, Y, Z. So X, Y, Z also have to match the names inside our code. Then after that, I just save this and we are done, right? So now our next step is to implement the design. Our next step is to implement our design. So all we have to do is come to implement here in the design flow navigator, run implementation. Yes. Okay. Takes a little time to implement the design. So you just have to wait for that little time. And then because we are just using doing and or XOR, this is very simple. So it won't take that much time. But once you're doing a huge design, sometimes it can take you days before the implementation is done. And if you made an error, it will take some number of days for the design to be implemented. And if you make a very simple error, you have to go back to your code, change it, and re-synthesize again, and then re-synthesize and re-implement again, and it will take more days. So designing is actually very very tedious, right? So you can see it running here. This point, it means that it's still running, and you can't do anything about it. So you just have to wait. Okay, now it's done. Come to click on generate file. You can actually open implemented design to see how it implemented the design. You can also view the reports to see the reports of the implemented design. But we just want to generate the bitstream. This bitstream is what will be uploaded onto the FPGA board. So just come to bitstream, generate bitstream, click on OK, OK, and it begins to generate our bitstream. So running bitstream, run and write bitstream. It's still generating the bitstream. Now, after the bitstream is generated, you just go to open hardware manager. You want to program. Okay. So now here we have to actually connect our FPGA board. So this is our FPGA board. You have to connect the USB cable to the FPGA board here. Connect it and then connect the USB port to your computer. Right. So you connect this to the computer, and then we connect the FPGA board, and then we switch it on. Right. We switch it on. We have to first of all switch it on before we can actually program it. So this is being switched on. Right. So next is um, the open target, and then go to auto connect. It will discover the FPGA device here. Right. It will actually discover the FPGA device. If it doesn't, then it means that your connection or your port has an issue. Then you can change ports or work on your ports to make sure that it works. So this is the FPGA device it has um, discovered. this FPGA device that is covered. So you can just come here and click on program, and then it will navigate to where the bit file is stored. Right, this is the gate.bit. So that is the bit file we're going to use to program this FPGA board, right? This FPGA board, right? That's the bit file. So just click on program, and if the LED here is on, it means that it is done programming. So it means that now we can use our buttons here, our switch buttons here, and then means that now we can use our buttons here to actually control our inputs and outputs. So now the buttons are all 00. So the LEDs here are all 0000. So you see that they are all off, right? Because now our truth table says that if A is 0, B is 0, X is 0, Y is 0, and Z is 0. So now let's test for our last is this 1 and 1. So let's switch on our dip switch here to be 1 and our dip switch here to be 1. So now A is 1, B is 1. So it means that you have X is 1, Y is 1, Z is 0. So our LED, our third LED here is 1, right? Our second LED is 1, and then our last LED is 0. So it means that we'll be able to program um, our AND or XOR gate on this FPGA. So that's how it's done simply, right? So that's the end of this lecture. Thank you.